Hi guys, so this is coming from chapter 7 slide presentation, and if you are going over the slide presentation, this is slide number 10 where you discuss work done by gravitational force. Now I am going to draw the same picture that appears on the slide where you have an object, and the object has a gravitational force pointed in the downward direction. You guys know that Fg equals to mass times g, and from point A it is going up, so the displacement is happening in the upward direction, and let's say the displacement is d, and it goes to a point B. Point B. Now if you are looking for the work done going from A to B, well, the work equation is force dotted to displacement. And so if you expand it, you will get F d cosine theta. Actually in this case it is F g. And then when you look at the Fg, Fg equals to mg. So you substitute for mg, then d cosine, and the angle between the two vectors. Fg is pointed downward, d is pointed upward, and the angle between the two is 180. So you substitute the theta by 180, and cosine 180 is nothing but minus 1. So you end up getting mgd times minus 1. W A to B therefore equals negative mgd. So that is the work done by the gravitational force when going from A to B. And then we are looking at the situation going from B to A. So let me mark B first and then A, and the same object. Now the gravitational force is marked downward, and the displacement is also coming in the downward direction. So if you write down the work equation going from B to A, now you have F g or F dotted to D, the same equation as before, and then you have Fg d cosine theta. Now again we are looking at what theta is. So let's mark Fg and D. They are parallel, pointed downward, and when two lines are parallel, the angle is 0. You already know that. Cosine 0 is 1. Therefore, if you substitute for Fg, which is mg, mg times d, and that's the answer for work going from B to A. So you can put a box around that. And then this is how the gravitational force, work done by the gravitational force works. And depending on the direction of the motion, things actually change. And then the next thing is where you need the knowledge of integration. Now first we can look at the general equation. Where you have the work done by a constant force, and the work can be written by F dotted to D. Now in slide 14 you can see that we are looking at the work done by a variable force. Now work done by a constant force, it is already discussed. Right above you can see that. And first let's look at what a constant force is. So F equals to 10 Newton is a constant force. F equals to negative 2 Newton also is a constant force. So let's say the first one is going along I hat direction, which is x, and the second one is going in j hat, that means along y direction, negative j hat means in negative y direction. Now the work done by a variable force, meaning there you have a something that is changing. It can be time, it can be distance. That is actually the case for the most of the time, most of the part. So fx, f as a function of x can be written as 3 times x, unit is Newton. And then you can have something like f as a function of y. There you have the unit actually doesn't change no matter what you have in the force, and the unit stays as newtons. Now if you are to look at the work done by a force like this, then we need an integration. So for example, xi going from xi to xf, and the force as a function of x dx. That is the equation we need to get the work or to find the work here. Now this equation can be put inside a box, and if it is fy, then you have to do the integration going from y initial to y final, and then with dy. So earlier we had work equals to f dotted to d, and there you have, down here we have work equals to the variable function dotting to the variable, which in this case the variable is x, and we are taking the dot product with x, but you don't really see the dot product because x and dx, they are both in the same line, and the angle becomes cosine 0. Cosine 0 is 1. So now we are looking at the spring force. The reason that we are looking at the spring force is because it is a variable force. So Fx is given by negative kx, and that is what is called as the Hooke's law. Perhaps you have already heard about the Hooke's law in your lab. And in this case, k is called a spring constant and x is the displacement. So now I am going to elaborate the force on a spring. So let me first draw a picture of a block attached to an object attached to a spring. So this is the spring, and at the end of the spring you can see a block attached to it, and at the position where the block is, I take the position as x equals to 0, and then I am expanding the spring. So when you are expanding the spring and it is still on a surface, for example, and the distance that it expanded is on the or toward the rightward direction, and the rightward direction, the expansion or the displacement in this case, you can take it as d. So when you are expanding a spring to the rightward direction, the block experiences a leftward force, and that leftward force is what is called as a resistive force, and that is why you see a negative value in front of Fx. And by the way, k is called the spring constant, as I mentioned earlier. So whenever you are moving leftward, there is a force to the rightward direction. When you are moving in the rightward direction, there is a force in the leftward direction. So the negative sign indicates a resistive force. That's basically the idea of the Hooke's law. Now let's take a compression. Now the spring is compressed instead of an expansion. Okay, so you can see that from the equilibrium position, it has moved in the leftward direction. So the equilibrium position was the point where you have the top topmost picture where x equals to 0. And now the spring is compressed by an amount of x or d. It doesn't matter what letter that you are using. So as you compress the spring, the block actually experiences a force F in the opposite direction. So the compression happens in the leftward direction, but the force is pointed in the rightward direction, and this is what is called as a resistive force. I hope you understand what it means by the resistive force at this point. The expansion to the left, or I mean to the right, the force is experienced in the opposite direction. Now work is given by x initial to x final, and in this case fx dx. As I said, y, or it can be y or t or whatever you want, right? But in this case it is x. So the limits are x initial to x final. Fx is minus kx and dx is the one that we are integrating over. So negative k comes out of the integrand, and you put xi, xf, those are the limits, and then you have x dx inside. So negative k, and when you are taking the integration, that becomes x square over 2, and the limits, upper limit is xf, lower limit is xi. So as you guys know, those who have done calculus, minus k, we substitute the upper limit first for the x, and then you write it, and then you substitute the lower limit xi square, and then divide by 2, and then you write the whole thing like that. So when you distribute negative k, it becomes negative k xf square over 2. Negative negative becomes positive, and you have x kx initial square divided by 2, and that is our work. So work equals, if you write it or rearrange it in such a way that the negative comes to the middle, you have 1/2 kxi square minus 1/2 kx f square, and that is our work equation for a variable force. So I hope you understood that, and this is what is called as the work done, or this is how you write it, work done by a spring force, or work done by a variable force. And unlike in previous cases, here you have x initial, or the initial component in the beginning, because there was a negative sign that we had to deal with earlier. So we can do a little example where we have a spring with a spring constant 300 n over m, and the spring constant is k. So k equals 300 n over m. N over m is Newton over meter, and Newton over meter is the unit in this case. And there is a block attached to a spring, as we discussed earlier, and the x equals to 0, that is the initial point, and then it is expanded to a point x equals to 5. And we are supposed to find the work done by this, what is the work done by this, by the spring when it is expanded from 0 to 5. So we know that the spring force is negative kx, but k is given to us as negative, not negative, just 300. So f becomes fx equals negative 300x. All what we did was substituting for k. Now we can start over. Either you can just use the equation we derived, or can start over. Since we are learning this for the first time, I am doing all the work from the beginning. So let's write it down. 0 to 5 integration negative 300x dx, and negative 300 comes out of the integrand, and going from 0 to 5, x dx, and then you do the integration, negative 300 outside, x square divided by 2, and the lower limit is 0, upper limit is 5. So we substitute the upper limit first and then subtract the lower limit. So 5 square over 2, and the lower limit is 0. You don't have to do that since it is 0, but I'm just doing it so that you can actually see what I am doing. You can follow what I am doing. And then negative 300, and 5 square is 25, divide by 2. And that's basically the answer. Work done when the expansion happens from 0 to 5 for a spring that has a 300 Newton over meter spring constant, then the answer actually becomes a large value. That would be negative 150 times 25. And that answer is in joules, or sometimes people write it as Newton meter. And this is the final answer as calculated for work. So I believe that you understand what we did so far. The integration part, if there is someone who is not quite familiar about the integrations that we have done here, this is actually the simplest form of integration that anyone can do. We can talk about that in the class next time we meet. Okay. So there is an assignment on Blackboard. Please do that. I mean, there are 4 questions. The first 2 questions are calculus based, meaning integrations, and the second 2 questions are directly coming from the non-calculus part of this lecture. And we need this going forward, so please don't forget to go over this lecture because I am not reteaching this. Okay. All right, see you on next week. චූටි පුතේ, දැන් අම්මා මෙතනින් ගියා විතරයි. ඔයා ගියාද? I finished reviewing it. ඇත්තට පුතේ? Yes.